All right, everybody. This week, there's only really one big topic this week, but it's pretty difficult to understand. Um, I've always had a tough time with it, honestly. But I think it's an important topic, and it's one that we really need to discuss. And it's the idea about Bayes' theorem and the confusion of the inverse, which they talk a lot about in the chapter this week. So what we'll do is we'll go through it in this lecture, and then in our check-in, we'll talk about it more. And I've got a problem at the very end for you to work through on your own, which is kind of related to how this would update over time. All right, so this week it's about thinking rationally about uncertainty. And so just a quick overview of what we'll talk about. We'll talk a little bit about how we estimate things, which is just a little bit of a review of how we've thought about it and talked about it already in the course. And then we'll ask this question and try to answer it by looking at Bayes' theorem, which is there a rational way to estimate or to update our beliefs? So if we find new information, is there a rational way that we can incorporate that information into what we previously thought, which are called priors in Bayes' theorem? So we'll look at this and we'll talk through it. And I've got a problem that we'll actually work through together, and I've broken it down into detailed steps. So how do we estimate? We've talked about some different patterns or different methods earlier, right? It's kind of just a pick a number thing. We've talked about anchoring and adjustment and how an anchor can change what we estimate and lead us and hold us basically in place near the anchor. We've talked about this bias that we have where we tend to underestimate common things and we tend to overestimate rare things. And we've looked at problems for both of these, right? So anchoring and adjustment, the problem is you don't tend to correct yourself enough. You tend to undercorrect. And so the anchor holds you in place. The other problem is that there's a systematic bias, right? Where we tend to think of rare events as being more dangerous or more likely than they actually are. And we tend to think of common events as being less likely than they actually are. And so wouldn't it be great if we could look at data and use some kind of mathematical formula to actually get to a precise level of accuracy? And that's what Bayes' theorem is about. So let's look through it. We're going to answer these questions, right? Is there an objective way to estimate? And there is usually, especially if you have some data. And is there a rational way to update your beliefs when you encounter new information? So you have already an estimate and you've arrived at it by looking at data. Well, how would I encounter or incorporate new evidence, right? That would maybe change or should change my beliefs. So we're going to work through a thought experiment on this. Before we get to the thought experiment, I wanted to point out an interesting kind of phenomena related to estimating probabilities, and it's the Monty Hall problem. I'll post these two videos in the weekly playlist, but this is a really interesting problem, and it kind of points to how probability estimates can be strange to us, and they're not intuitive at all. And so you know, if we realize that we can't deal with this stuff intuitively, right, using our system 1 processing, then we need to develop rules and methods for dealing with it with deliberative processing. And so that's what we're going to look at. All right, so here's the thought experiment. Imagine there's a rare form of cancer that affects 0.01% of the population. So that's 1 out of every 10,000 people. And so not a very common disease. What would be your estimate if, based on this knowledge, that you would develop the disease or that you have the disease? If you're dealing with this objectively, you should estimate, you know, using what the data is, right? So what's the probability that I have the disease? Well, 0.01%, not very likely. 1 out of 10,000, not a huge probability there. All right, so we've talked about what our original estimate would be, right? So if we know that a disease has this type of commonality in the population, it affects 1 out of every 10,000 people, then that's what we're going to start with. That's my prior belief. What is the probability that I have the disease? 0.01%, or 0.0001 if you write it out entirely. And so let's continue this thought experiment. Okay, so there's a test that can detect this disease, and it is correct 99% of the time. So if you have the disease, It tells you you have the disease 99% of the time. And if you don't have the disease, the test comes back that you don't have the disease 99% of the time. So, you know, those are pretty good discriminating tests, right? A 99% accurate test. Now let's say you take the test and it comes back positive. How likely is it that you have the disease? And so what we're seeing here is this kind of temporal event, right? We're starting at 0.01% probability that I have the disease. I take the test is positive. Now, where should I be at the end? What is the probability that I have the disease now? A lot of people would look at this and say, well, if the test is 99% accurate, then the probability that I have the disease is now 99%. But in fact, this is not correct. It is not accurate that you have a 99% probability. And we're going to talk about why that's not accurate, and we're going to talk about what the true probability is given a single test on this and it coming back positive. All right, so why is it not accurate to assume that it's a 99% probability? Well, there's a couple of reasons. One is medical diagnoses, and any test that's a diagnostic test is going to have error associated with it. What does that mean? Well, sometimes they tell us the wrong result. Sometimes we have the disease and it tells us we don't have the disease. Sometimes we don't have the disease and it tells us that we do. And so there are two different ways to be wrong in this diagnostic test. And now let's take a look at what those two ways are. All right, so for an example that is more maybe commonly used, let's think about a pregnancy test, right? And so when my wife and I were trying to have our first child, we were, taking pregnancy tests and seeing if she was pregnant or not. And so there's this state of the world, right? That either she was pregnant or she was not pregnant. Now, if she takes the test is going to be independent of this. The test is either going to come back positive or negative. Now, how might the test come back? Well, let's take a look. Now, if you're really pregnant and you take the test and the pregnancy test is positive, that's a correct judgment. And that's also often called a hit within the literature, but that's correct, right? Good job, test. My wife is pregnant and you said she was pregnant. However, there are occasions, right, where the test might not pick up the pregnancy. And so you think you're actually pregnant, right? But the test says negative. And so this is an incorrect or an error, right? Test is wrong. And this is a specific kind of error. It's called a type 2 error or a false negative. It's a negative test, but it's false because you really were pregnant. Now, so this is one area to be wrong, right? There's a type 1 error. That's one way to be wrong. There's also the, type 2 error. There's also the type 1 error, though, which is a false positive. This occurs when you're not pregnant, but the test is positive. And so that is a false alarm. It's also wrong. And so this is our second way to be wrong. So there's two ways to be wrong here, right? You can be pregnant and get a negative test, and that's a type 2 error, or you can be not pregnant and get a positive test, and that's a type 1 error. There are also two ways to be right? You're not pregnant and you get a negative pregnancy test. That's a correct judgment again, and we call that a correct rejection. So when we take tests, right, we have to realize that we have hits, we have correct rejections, we have false alarms, and we have misses. And so each one of these, right, is where the test could be, right? And so if we take a positive test, I don't know where I am. I take a test that's positive, am I in this group right here, the correct group, or am I in the false alarm group? I don't know. Similarly, if I get a negative result, am I here in the miss group, or am I over here in the correct group? And so anytime there's a test that is positive or negative, right, there are different places that you could end up. This is just a silly example of this. that's in a comic form that I think is kind of funny, and I show it in my research methods classes, so I thought I'd show it here as well. So type 1 error, doctor telling a man you're pregnant. Type 2 error, doctor telling a woman who is clearly pregnant you're not pregnant. And so those are the examples of type 1 and type 2 error. Okay, so this idea of false positives and false negatives comes into our thought experiment that we need to think about, right? And so there's a rare form of cancer that is 0.01%. We know the test is accurate 99% of the time. You take the test, it comes back positive. How likely is it that you have the disease? We have to update our prior belief, and we can do this with what's called Bayes' theorem. And so what we need to find out here, and what we're really asking is, okay, I know my test is positive, but what is the probability that that's a true positive and not a false positive? So what is Bayes' theorem? Bayes' theorem is a mathematical proof that, or theorem that Thomas Bayes came up with in the mid-18th century. So in 1740 or so, Thomas Bayes, this guy figures out this thing that, hey, I can objectively update my prior beliefs every time I encounter new data, if I know certain things about it. And so Bayes' theorem describes the probability of an event based on prior knowledge of conditions that might be related to the event. So, for example, what is that prior knowledge? Well, it might be how common is the event in general. It might be how diagnostic is a test, right? You can use all sorts of information in this, but it's all about conditional probabilities. What is the probability that I have cancer without the test? That's my unconditional probability. Now, what is the probability that I have cancer given that the test came back positive? This is the condition, given that the test came back positive. It means I've taken the test and the test is positive. And now I want to know, given that, given the positive test, what is the probability that I have the disease? So what is the probability of the disease given a positive test? And this is our conditional probability because we know one of the conditions. The condition is that I've already taken the test and it's positive. And so now I'm trying to reason and say, well, what's the probability that I have the disease? How concerned do I need to be? How much should I be freaking out right now? So this is Bayes' theorem, and it divides the final probability, right, which we can think about, into a section here. And so we've got a division here. And so if we look at each one of these, right, we can see what each one of these terms is. So A is essentially the disease, and then B is essentially the test or not. This symbol right here that looks kind of like a backward 7 means not. And so if we were to read this, we can read this in a specific way, right? This P parentheses A dash B means what is the probability of A given B, and that is equal to this formula, the probability of B given A times the probability of A, and then divided by the probability of B given A times the probability of A, plus the probability of B given not A times the probability of not A. And so what is A? That's our prior probability, the initial degree of belief in A. We can call that the probability of disease in this example. So what is the probability of not A? Well, it's the inverse, right? It's the probability of no disease. And so if whatever A equals, right, we know that not A has to equal 1 minus A, because the total amount of probability is 100%. You can't be higher than 100%. And so here, right, the probability of having the disease is 0.0001. And so that means we know that the probability of not A is equal to 0.9999. All right, so we've got the probability of B given A is true. So what's the probability of a positive test given the disease? And that's in the study, or that's in the example as well. We've got the probability of B given not A, the probability of a positive test given no disease. All right, so what do we have here? This positive test given the disease. That's a true positive, right? Or a hit. Probability of a positive test giving no disease. This is our false positive. And then lastly is what we're solving for is this, the probability of A given B, right? So what's the probability of a positive test given the disease? That's our true positive. What's the probability of a positive test given no disease? That's our false positive. And so identifying these terms gets you halfway to solving the problem. So let's look forward and start working through the problem. If you don't get it yet, we're going to solve the problem in two different ways, and so hopefully that'll help. But one thing to notice right now already is that what we're doing here is we've got a ratio, right? We've got a ratio of positive tests given the disease over total number of tests. And so that'll make sense in a bit when we work through it in the second way. All right, so here we are, we're at the beginning. There is a rare form of cancer that affects 0.01% of the population, 1 out of every 10,000 people. So let's go forward to our chart of positives and negatives and false positives and false negatives and figure out where that goes. All right, so where does this go? There is a rare form of cancer that affects 0.01% of the population, 1 out of every 10,000 people. So that goes up here in the very top columns, right? So it's dividing the columns up, right? So the total for everything that falls under this column all the way down here, right, is 0.01%. And the total for this column is 99.99%. So we've already started to define this, right? So the probability of A is 0.01%. The probability of not A is 99.99%. Okay, so let's keep going. There is a test that can detect the disease and it's correct 99% of the time. If you have the disease, it tells you that you do 99% of the time, and 1% of the time it says you don't, right? That's just a logical extension of that, right? So let's look back into our chart and see where does that go. All right, so we know we're in this column because at the beginning it says if you have the disease, it tells you that you do 99% of the time, and 1% of the time you don't. So we know that when we have the disease, 99% of our results are going to be correct, and 1% of our results are going to be incorrect. So this is the probability of the disease given a positive test. Or excuse me, the opposite, right? B given A. And this is B given not A, right? So positive given the disease, positive given not the disease is how to read that. All right, so we know we're in this column because it says if you have the disease, right, we're here. It tells you do 99% and 1%, all right? Now, if you don't have the disease, it tells you that you do not 99% of the time, and 1% of the time you do. So let's go back to our chart and see where we are again. All right, so we know we're over here. If you don't have the disease, it tells you that you do not 99% of the time. So I don't have the disease, I get a correct rejection 99% of the time, and that means that 1% of the time I get a false positive because I don't have the disease, but the test tells me that I do. Okay, so let's see. Where are we now? You take the test and it comes back positive. What portion of positive results are true positives, right? That is what we're trying to figure out here. We're trying to figure out, I know I got a positive test, but where do I fall in my chart? Do I fall in the true positives or do I fall in the false positives? I don't know. I've only taken the test once. So what should my new belief be about whether or not I have the disease? We can answer this with Bayes' theorem. All right, so if you have the disease, it tells that you do 99% of the time and 1% of the time you don't. So here we are, right? We know this. We know that I've gotten a positive test. And so I'm trying to figure out, well, where am I? Am I here or am I here? And so I need to take, right, remember that this was 1% of the time, and this was a correct rejection 99% of the time. I'm trying to figure out, okay, I know I've got a positive test. Where am I here? Right? And so I can use the information in this chart to figure this out. All right, so if we plug it into Bayes' theorem, we've identified all of these things, right? We've identified the probability of B given A is true, so the probability of a positive test given the disease is 99%. We have figured out that the probability of A, right, the prior probability, the initial degree of belief in the disease is 0.001%. And so note that this portion of the formula is repeated in the denominator, and so we can just do that as well over here, right? So we just copy that down here. Now, the second portion, right, the probability of B given not A, we know that's 1%. That is the probability of B given not A is true. So that means that the probability of a positive test given no disease is only 1% chance, and the probability of no disease is 0.9999, because that's, again, right, the disease is only affecting 1 in 10,000 people. That means it's not affecting 9,999 people out of 10,000. So if we do all of this math, we should update our belief, and we should now be about 1%, right? 0.009804 is what you get from doing this calculation, which is about 0.01, which is about 1%. So what's the probability that I have the disease given this positive test? Only 1%. Now, you might think that this is low given how diagnostic the test is, right? The test is 99% accurate. But what we have to take into account is what is the general number of people that have the disease versus don't, right? How many false positives are there compared to true positives? And so this is 1% here. And so it might seem low, but it's actually kind of a huge jump, right? We've gone from 0.0001 all the way up to 0.01. So it's a huge increase in my probability, but it's still a low probability. And so that's what's really important about Bayes' theorem and to look at. All right, so now we're going to go through it a second way. We're going to look at it more symbolically now and why this works out to be the case that it does. All right, so let's work through this pie or this figure and see what's going on. So at the very top here, we have a group of people. Let's say it's 1 million people in total, right? All right, so how many of this 1 million people would we expect to have the disease, and how many would we expect to not have the disease? Well, we know that the disease affects 0.01% of the population, and it doesn't affect 99.99% of the population. So if we break these people out, we can break them out into a group that doesn't have the disease. 999,900 people do not have the disease, because that's 99.99% of this million. And we can see that there's 100 people that do have the disease, right? That's 0.01% of the population. All right, so this is our group that does not have the disease. This is our group that has the disease. Now let's give all of these people, all 1 million people, the test and see how many, what's being missed and what's being detected in these tests. So the test finds 99% of positive cases, and it finds 99% of negative cases. So let's look at that. So we give the test to all 999,900 people who do not have the disease. Well, 989,901, which is 99% of that total, will not have the disease, and their test will become negative. Their test will show that they don't have the disease. But out of this 999,900 people who do not have the disease, there are going to be some false positives. Now, how many false positives? 1% of this group will come back as a false positive. And how many is that? That's 9,999 people will have a false positive here, which is a lot, right? Like 1% of this, that's still a really big number, right? So we've got almost 10,000 people who don't have the disease, but will test positive for it. All right, so what's going on the other side of the equation? Well, over here we have our 100 people who have the disease. Now, if we give the test to them, 99 of these people are going to have the disease and get a positive test. So these people have this rare form of cancer, and the test shows that they have the rare form of cancer. Now, unfortunately, right, the test only detects 99% of positive cases. So that means that one person who has the disease will actually test negative here. This is our false negative. And so the question that we're answering with this is, all right, I know I got a positive test. So what is my percentage of being having that be the case that I'm actually a true positive. And so I need to find a ratio. I need to find a ratio of true positives to all positives. And so what is that ratio? Well, that is, what is the probability of this? It's how many true positives do I have? I only have 99 true positives. How many false positives do I have? Total positives do I have? Well, I have the 99 true positives, plus I have the 9,999 false positives. And if you do this math, right, to get the percentage here, you get that same number that we calculated using Bayes' theorem. And so it's 99 over, 10,098, right? And that gives you the 0.009, or approximately 0.01. And so when you're looking at these test results, you have to realize what I'm really looking at here is I've got a positive test. Now, am I part of this group, this smaller group, or am I part of this larger group? And that's the question that we're answering with Bayes' theorem. All right, so why is this idea most important, or where is this idea most important? Well, one, it's screening for rare events, right? The example that we've looked at shows that if you have something that's really rare, doesn't occur very often, you need a test that's going to be incredibly accurate for picking it up. Because otherwise, right, you're going to have your number of true positives being outnumbered by your number of false positives, which is what we saw here. Now, the other thing it shows is that this idea of the confusion of the inverse, right? So a lot of people would look at this equation, look at this and say, oh, well, the test is 99% accurate. That means there's a 99% probability that I have the disease, right? We've just worked through the math and the symbolism that's associated with it to show that that is not the case, right? The probability of B given A is not the same as the probability of A given B. Lastly, the reason this is really important is you can use Bayes' theorem to continuously update your beliefs in a more objective manner. And so I want you to try that for yourself, right? Using the same data that we looked at now, what is the probability that you have the disease if you have 3 positive tests in a row? So we now know the probability of 1 positive test, all right? So we can take our new information and re-enter it into Bayes' theorem and update our beliefs again. So see if you can figure this out, and we're going to work through this in our class on Wednesday for our check-in. All right, that's it for this week. Be sure you watch the other videos on the Monty Hall problem as well.